The next part of 10.5 deals with arc length. Now, we've seen arc length in both rectangular form and parametric form, and now we're going to have arc length once again but in polar form. So if we have a continuous function, r equals a function of theta, and this function has a continuous derivative on some interval from alpha to beta, then the arc length can be calculated by integrating from alpha to beta the square root of the function itself squared plus the derivative of the function squared. Now, I shouldn't really have to explain this a whole lot. It looks very, very similar to the rectangular form, very similar to the parametric form, except now we're dealing with function of theta and the derivative of the function of theta. I like to think of this as r and the derivative of r with respect to theta. So you can think of, again, this function of theta, r is a function of theta, and then obviously the derivative of r with respect to theta. So it's a pretty straightforward formulation, and it really doesn't need to take, I'm not going to explain where this comes from. Doesn't take a whole lot of practice doing it to just jump in. So that's what I'm going to have you do. I want you to just jump in and try to find the length of the curve defined by r equals 8 over the interval from 0 to 2 pi. Push pause on the video and go ahead and do that. So we start with our arc length formula here. Arc length formula, S equals this integration. And we say, well, R equals 8. Let me scroll down there. R equals 8. Well, what's the derivative of 8 with respect to theta? That's simply 0. And so what we're going to do is we're going to plug in 8 for the f of theta, and then 0 for the f prime theta. And then we're going to integrate on the bounds from 0 to 2 pi. So we go square root of 8 squared plus 0 squared, all integrated from 0 to 2 pi. If you do the calculations, you'll end up with your calculator giving you about 50.27, which is actually 16 pi. Now, this is the calculus way of understanding one of the geometric formulas that we had. What is r equals 8? Well, r equals 8 is simply a circle of radius 8. If we go from 0 to 2 pi, that is a circle of radius 8 traveled all the way around the edge of the circle from one side all the way back to the original point we started at. So what this is telling us is that a circle of radius 8 has a circumference of 16 pi, which probably, if you remember from, basic geometry classes, the circumference is always twice the radius times pi, 2r pi. And you can see that this is always going to give you this regardless of which radius I chose. So there you go. That is the arc length of, in this case, a circle. So I'd like you to do those same formulations. I'm going to give you another example to find the arc length of. So find the length of the curve that we're given here, 4 sine theta, over the interval from 0 to pi. Go ahead and push pause on the video and try it on your own. All right, so we start with the formula. Integrate from alpha to beta, this square root. We're taking r equals 4 sine theta. That is our function itself, so that goes in for f theta. So that's what we go in there. And then the derivative of 4 times sine theta is 4 times cosine theta. So that goes in right here. Now you could do this one by hand if you wanted to, but it's a lot easier just to utilize our calculator. So integrate from, again, we integrated from 0 to pi. That was the interval we were given. 0 to pi, square root, 4 sine theta quantity squared plus 4 cosine theta quantity squared in that square root. And what we end up with is 4 pi, which again on a calculator comes out to about 12.57. And by the way, what we did once again was deal with a circle. And this is, in this case, this is a circle of radius 2. R equals 4 sine theta is a little bit awkward, but it is a circle of radius 2. Let me show you that on the graph. So you graph that, obviously 4 sine theta, circle of radius 2. Center is at 0, 2 in rectangular coordinates. And you can see one point is on the origin, interestingly enough. So there you go. Now what I'd like you to do is try this last example of arc length on your own. So find the length of one petal of the curve r equals 7 times sine of 5 theta. Push pause on the video and go ahead and do that. All right, so we start with the arc length formula once again. Alpha to beta, square root, same deal. We have r equals 7 times sine of 5 theta. If I take a derivative of sine is cosine, but since this inside function is not just theta itself, since it's 5 theta, I need to multiply by the derivative of the inside function. In this case, that's 5. So I'm going to get 5 times 7, which is 35 cosine of 5 theta. So that's my r prime. So I'm going to stick 7 sine 5 theta in for the f theta. I'm going to stick 35 cosine 5 theta in for the f prime. And now I just have to figure out, just like we did in the last video, what are the bounds that I choose from alpha to beta. What I chose is, whoops, that's not right. What I chose is from 0 to pi over 5. Now, you can think of this in a couple of different ways. The first way you can do it is you can, trace around stuff. So trace around, push graph on your calculator, graph it on your calculator, trace things around. The other thing you could do, algebraically speaking, is hopefully we understand a little bit about sine and when sine is 0. Sine is 0 when the angle is 0 or pi or 2 pi or 3 pi. So, well, we had 5 theta as the angle we were dealing with. So if we divide both sides by 5, when theta is 0 or when theta is pi over 5 or when theta is 2 pi over 5, you go through the origin. So I just picked the first two, from 0 to pi over 5. Now, when you plug that into your calculator, I ended up with 73.54. Okay. Now, is that a nice divisible thing by pi? No, it is not. Okay, it's not pi times a whole number or anything like that, like the other two examples were. But that's what we get. It's about 73.54. So that is how to calculate arc length in terms of polar coordinates.